So in this video, we're going to take a look at 12.2 and 12.3. Won't be doing all the sections, just kind of an intro to what we call polar coordinates. So to do that, let's start with our basic unit circle. And let's start with a simple angle that you're all aware of, pi over 4. Now, since this is a unit circle, my radius is 1. And we end up with, if you recall, 1 over square root of 2. So we end up with radical 2 over 2, radical 2 over 2 for our x and our y values. Where x is square root of 2 over 2 and y happens to be square root of 2 over 2 because we know we have this 45-degree angle here. Well, this is our rectangular system. That's our x. There's our y. Our polar coordinate system works a little bit different. We still draw these axes, but we don't really use them the same way. The way we use the axes is we actually use them first with the angle, kind of the way you're used to working in trigonometry. So we say that when the angle starts in the positive x, what you know is the positive x-axis, we start at 0 degrees. And then as your angle moves, this is of course pi over 2, that's pi, and 3 pi over 2. And let's suppose we ended up with an angle directly out here. This is the angle pi over 4. And we can have all kinds of angles around our axes. This angle here will be 3 pi over 4. And you get the idea, 5 pi over 4. And you would go all around. This one is 7 pi over 4. Okay, and then you would draw other angles. So you would have, much smaller angle would be pi over 6 would be here somewhere. Pi over 3 might be up there somewhere. And you have all the angles. Now, the other thing we work with is how far out on that angle is our point. So, for example, this value here is somewhere along this pi over 4 line. It's at exactly radius 1. So then I'll do this one in blue. At all of the marks of 1, we have this circle. Everything along here is radius 1. So there would be our point, square root of 2 over 2, square root of 2 over 2. It's in the same location. If you put the grids on top of each other, they'd be in the same place. It's just how you get to them is different. And how we represent it is different. So that's the point in blue. We use radius first. The radius is 1, and the angle is pi over 4. So let's do another point. Suppose I wanted 2 pi over 6. All right, pi over 6 is going to be a much smaller angle than pi over 2. It might be it's actually your 30-degree angle, so you can kind of picture where that would be. But instead of going out 1 unit, so there's 1 unit, I would go a second unit. So here might be the point 2 pi over 6, and so on and so on. There's also different ways to represent that angle, but before we do that, let's talk about what happens when either the r or the theta are negative. So we know where 2 pi over 6 is. Where would negative 2 pi over 6 be? Well, negative 2 pi over 6 is still going to be this same angle, but instead of heading out like we did to get here, we go in the opposite direction. 1, 2. So here we would have the point -2 pi over 6. Okay? Now, let's go back to a +2, but let's do negative pi over 6. That's going to change your angle now because your angles go in a counterclockwise direction. But if we do negative pi over 6, we have to go in our clockwise direction. So that would be here. There's 1 unit. 2 unit would be right there. That would be the angle 2, negative pi over 6. And then the last one, of course, would be -2, negative pi over 6. We already have negative pi over 6. If we make the 2 negative, again, we go out in the opposite direction. So if you look at actual grid paper for polar coordinates, what you're going to see is a whole bunch of concentric circles. This would be your 2, and they'd be labeled 2. This one would be 1. And so on and so on. So you can take any rectangular point and turn it into a polar, and you can also take any polar and turn it into a rectangular. So let's see how we do that with conversions. So we can convert our polar to rectangular, and we can convert our rectangular to polar. So let's talk about the equations we would need for each of those. They're going to come from a very basic representation, and that's a right triangle. If you take a right triangle built on your axis, this is your radius, this is your y, that's your x. We can get all these conversions directly to this right triangle. So from polar to rectangular means we're starting with polar coordinates and we want an x and y coordinate. So x, well, we know x represents cosine, right? But it only represents cosine on a unit circle. It's technically 1 times cosine, but because on a unit circle radius is 1, we don't have any number there. It's just cosine times 1. So to actually do conversions on something that's not a unit circle, x is equal to r times cosine theta, and then of course y is r times sine theta. So we can take a polar coordinate and turn it into a rectangular. So let's go ahead and do that with our 2 pi over 6. So x is going to equal 2 cosine of pi over 6. Well, if you can't remember what cosine of pi over 6 is, you need to draw yourself that little triangle. Put pi over 6 down here. And pi over 6 is the small angle. Remember, the 1 is across the small, that's a 2, and that's a square root of 3. These kind of help you where your calculator wouldn't, because your calculator is going to give you decimal approximations and not exact answers. So cosine of pi over 6 is square root of 3 over 2. So square root of 3. Now y equals r, which is 2 sine of pi over 6. So that's 2 pi over 6 in this case. Sine is 1/2. So that equals 1. So the polar coordinate of 2 pi over 6 is in the same exact location as the rectangular coordinate square root of 3, 1. Okay. To go in the other direction, well, now I need to figure out what r and theta are equal to, because I got to start with the rectangular. Well, look back up at this triangle up here. There's a real classic representation for r, one you are very familiar with. Do you see it? Yep, r squared equals x squared plus y squared. So what does r equal? Square root of x squared plus y squared. Now, theta, if you put a theta there, what's a relationship that links theta with just x and y? That would be tan. So if I solve for theta equals inverse tan of y over x. And these are the two that you would utilize. So for an example, you can take absolutely any possible point. Let's do, I don't know, 2, 5. We'll keep it simple. So r equals the square root of 4 plus 25 square root of 29. Theta equals tan inverse of 5/2. Yeah. It is not a pretty point. You could only get a decimal approximation of that tangent, but the point would be square root of 29 tan inverse 5/2, whatever that is on a calculator. As you can clearly see, some points are just much, much nicer when written as rectangular versus polar. And then some points are actually nicer when written as polar versus rectangular. So it really depends. The other thing that we can convert are actual functions. Or to convert or even sketch the graph of polar functions. So we'll sketch graphs first. Polar functions are kind of actually the prettiest functions you'll ever see. R equals f theta. So this is like saying y equals f of x. We just say y equals f theta. So there's some very basic functions. The same way you know, hey, sorry, if y equals 3, what kind of a line is that in your rectangular system? If y equals 3 and only 3, then you know you have some horizontal line at y equals 3. So what happens if we have a polar function that is simply r equals 3? That says the radius is always 3. Well, what do you know has the radius that's always the same thing? Right, that is a circle centered at 0, 0 with radius equal to 3. So any function is simply a circle centered at 0, 0 with radius equal to a. That's your most simple polar function. So let's get a little bit different. Instead of r equals a, what happens if the radius equals theta? Well, we got to do a little chart for that. Same way you do XY charts. What you do are theta R charts. So, I mean, you can pick theta 0. They're the same, right? So pick points that you know, or meaning angles that you know how to deal with. We could do pi over 4. Pi over 4, they're the same thing. We know pi over 2. We know pi. We know 3 pi over 2. All right, so essentially what's happening here? When you're at the polar coordinate, well, angle 0, radius 0, of course, 0, 0 is always still 0, 0, regardless. All right, angle, pi over 4, I'm going to go up to here. How far out am I going to go? Well, 3.14 divided by 4, it's a little less than 1, so I don't know. You know, if you got a circle, remember your polar paper will have this, you'd be like right there. Okay. I'll put some, here's 2, here's 3. I'll put some polar graph paper kind of out there. All right, pi over 2 is up here. Well, 3.14 divided by 2 is a little more than 1, so it's more up here. Pi is out here, and that's a little more than 3. So basically what's happening is you're increasing, and you're going to keep increasing as you go around, and you have what is called a spiral. So in r equals 3 theta, r equals 3 theta, r equals theta divided by 2, any relationship like that, what you have is a spiral. Now let's start to put some trig functions in there. Let's do r equals 1 plus sine theta. There's like 1, 2, 3, 4, 5 classic curves of polar functions. We've seen a circle, we've seen a spiral. Let's take a look at this one. What if we add something to a sine function? Again, this is where you can kind of play with graphing polar coordinates. Use points and theta values you're familiar with that you can plug in for sine. I'm just picking some. And if you haven't figured it out by now, the unit circle is going to play a really important part in what we're doing. So we want to go to pi, maybe we'll do something in between here. So I'll do like 3 pi over 4. Okay, and so on and so on. We'll go back to 6's, 7 pi over 6. I'm just picking angles that will work nicely with sine. Okay, so now all I want you to do, plug in 0, plug in pi over 6, plug in pi over 2. Keep plugging in numbers. You can hit pause, plug in all the values that you can think of. Oh, let's keep it all pi over 6. Let's just keep it consistent. Sorry. I was going to do 3 pi over 4, but let's keep it as 5 pi over 6, slightly less than pi, so we have consistency. So when I plug those values in, 0, sine of 0 is 0, 1 plus 0 is 1. Sine of pi over 6, that's a half, plus 1 is 3 halves. Sine of pi over 2, 1 and 1 is 2, and so on and so on. So you get the idea. You can go ahead and you'll start to see a little pattern. And then you come over to your polar grid and you kind of start to graph them. And you see they come out a little bit, right? Oops. It's symmetric, right? Pi is 1 again. And then they kind of quickly come in. Instead of 1.5, we're only getting a half. Sorry, I don't know why it keeps happening. And what it does is it pops up here. Hello? Forgot to hit pause before I answered my phone. So you can see when you get to these 7 pi over 6 in quadrant 3 and 11 pi over 6, you're only at a half, so you're much smaller. And then it kind of comes back. I didn't put 3 pi over 2 in here, but if you do 3 pi over 2, we're going to come to 0. So this is actually called a cartoid because it's called that because it kind of is shaped like a heart, so they're called cartoids. Sometimes you get little loops inside of them, but that's another classic shape. So one more classic shape that we'll look at, and this one has nothing added. Instead, we have something multiplied. So this one I'll kind of explain to you. So you can even call this f of theta. It doesn't have to be called r equals. So here's the deal. This number represents the furthest that any petal is away from your origin. All right. And this value represents the number of petals. And I'll talk about petals in a minute. And basically, if that number is even, you double it. And if it's odd, you use exact number. So what does that mean? 3 sine of 2 pi. All right, so I need radius 1, radius 2, radius 3. That 2, because it's an even number, I'm going to double it. This is a flower graph with 4 petals. The petals, because it's a sine function, are just going to look like this. Boom. They're going to go out to 3, 1 in each quadrant, and there they are. Now, if I changed one little thing and turned it into a cosine, what that does is puts the petals around the origin as opposed to in between in the quadrants. So cosine graphs, the petals wrap around the origin, and on the other graphs, they wrap around, they're inside the actual quadrant. So for example, f theta of 2 sine 4 theta would actually have 2 looped in each quadrant. I can't draw really well, right? And each of them will go out to 2. So that would be a unit of 2. So you can kind of play around. If you're going to play around, I suggest playing around with these in Desmos. You are going to write the function r equals, and then you're going to write out the word theta. Please make sure you are in radians, and you can click the polar coordinate looking system inside the settings. But I suggest you can kind of play with these functions. You can also get any of these by, of course, creating that table of values like we did before. Now, the same way we converted coordinates, we can convert equations. So what does that mean? Suppose I had x equals 2y squared, and I want to convert to a polar equation. Well, what do we know? We know x equals r cosine theta and y equals r sine theta. So put in r cosine theta for x. Now I need to square this one because r is being squared. Squared. So to get my function, I want to solve, so I'm going to get rid of r squared on this side. Actually, that doesn't work, so get rid of r on that side. Now I'm going to get r by itself, get rid of 2 sine squared theta. So I have 1/2. I'm going to break this up. I'm going to make it a cosine over sine times a 1 over sine equals r. All right, so wouldn't that be 1/2 cotangent theta cosecant theta? So x equals 2y squared actually is the same equation as r, or we can call it f of theta equals 1/2 cotan theta cosecant theta in the polar coordinate system. And in the same way, we can take any kind of, I don't know, let's do r squared equals 4r cosine theta. And we can turn that into rectangular coordinates. Well, what is r squared equals? We know what r squared equals. That's x squared plus y squared. What is r cosine theta? R cosine theta is x. There it is, done. You don't need to do anything else with it. So it's pretty easy to convert your equations back and forth. So the last thing is called the calculus of polar equations. Okay, so to start this, we know that r equals function of theta. That's just how you write function, just to do our function notation for coordinates. We also know that if x equals r cosine theta, y, of course, equals r sine theta. So we can replace those r's. X equals f of theta cosine theta, y equals f of theta sine theta. So why am I doing this? I can graph a polar function, right? There's a nice simple rose one. Suppose I wanted the equation of a tangent line. Well, to get to an equation of a tangent line, well, we need some information. The main piece of information we need is a point, which of course will be given the value of the point, or a way to get that. We need a slope. To get a slope, you need a derivative. So, how do I get the derivative of these functions? Well, let's figure that out. dy dx. The problem is I have this secondary parameter, like we learned of parametric equations, called theta. So wouldn't it be true that dy d theta times d theta dx actually equals dy dx? Because you can cancel out the d thetas and you have dy dx. Now, if that's the case, wouldn't it also be true, instead of multiplying by d theta dx, because d theta dx really doesn't help us, I can divide by the reciprocal dx d theta. Well, all right, let's talk about the first one, dy d theta. That's just going to come from here. This is, remember that thing from Calc 1? A product of one function times another. And we call that the product rule. So you can find dy d theta by first taking the derivative of the first function times the second function plus the first function without the derivative, and the derivative of the second function. Well, I know what the second function is, sine. The derivative of sine is just cosine theta. Okay? Now, do the same thing over here with the x1. Derivative of the first. Here's where you got to be careful, because in that second piece, when you take the derivative of cosine, you actually get negative sign. So we're going to pull the negative out here. And this formula is how you get the derivative of a polar coordinate. So let me go back to my black ink here. Let's look at an example. Suppose I want to find the tangent line to r equals 4 sine 2 theta for theta equaling pi over 6. Well, to do that, couple things I need to work out. So if f of theta equals 4 sine 2 theta, we're going to do a little work here. What would f prime of theta equal? Because I'm going to need that. Well, wouldn't that be 8 cosine? That's not squared. That's a 2. Of 2 theta. Why is it 8? Because I applied the chain rule. Sine of 2 theta is cosine 2 theta times the derivative of 2 theta, which is just times 2. So the 4 becomes an 8. Now, to make this job a little bit easier, I'm going to go ahead and evaluate a few things. I'm going to evaluate what f of pi over 6 is. And the sine, right? If you don't remember you can put your triangle out there, right? You're going to need pi over 6, and you're going to need pi over 3. So pi over 6 is a smaller angle. That's a 1, that's a 2, that's a square root of 3. Sine of pi over 3 is 1/2. So 4 times a half is 2. F prime of pi over 6 is 8 cosine 2 pi over 6, which is 8. Cosine of pi over 3 is square root of 3 over 2. The other things that'll come in handy we'll get from the triangle. All right. So I worked all that out so I don't have to work it out when I'm doing problems. So what is dy dx? Well, dy dx, it's up at the top of the screen there, is going to be f prime of theta. Oh, I just calculated that to be, I know what I did. This is wrong. Hopefully you caught that mistake for me. I needed cosine of pi over 3 because I had to multiply it by 2, not pi over 6. So cosine of pi over 3 is 1/2. So that answer is 4. Let me make sure I did, yeah, up here as well. Sine of pi over 3 is actually, sorry about that. Sine of pi over 3 is square root of 3 over 2. Oh, I did have that 2 radical 3. Okay, let's just make sure we got those correct. All right, so dy dx is f prime of theta. Oh, that's 4 times sine of theta. Remember, theta is pi over 6, so that's 1/2. Plus f prime of f of theta, just f of theta, which is 2 radical 3 times, I'm up here, cosine of theta. Cosine of pi over 6 is radical times radical 3 over 2. We'll clean that up in a minute. Denominator, f prime of theta again, of course, is just 4. Cosine of pi over 6 is square root of 3 over 2 minus 2 radical 3 times, now this is the 1/2 goes here, sine of theta. All right, let's clean it up. I get 2 plus radical, the 2's cancel, 2 plus 3 over 2 radical 3 minus radical 3. So it looks I get 5 over radical 3, which if you rationalize it, that's my slope. So to finish the tangent line, you need a point. My polar point, right, is r theta. And where's this is occurring? Well, this is occurring at pi over 6. Well, what's my r value at pi over 6? Just go back to your original equation, which was 4 sine 2 theta. So r is 4 sine pi over 3. And sine of pi over 3 squared root of 3 over 2. So it's 2 radical 3. So my polar coordinate is 2 radical 3 comma pi over 6. We need to convert that now to rectangular, because I want to put my equation of my line in xy form. So x equals radius cosine pi over 6. And if you do all that work, it comes out to pi over 3. And y equals radius sine pi over 6. And if you do all that work, you get 3. So now what do I got? I got a slope of 5 square root of 3 over 3, which is what we found when we did all that, at the point radical 3, 3. And all you need to do is plug it into your equation. Do a little work. Radical 3 becomes 3. 3's cancel, minus 5. Right? Because radical 3 becomes 3. Cancels with that. You get minus 5 plus 3. And you're done. Okay. Area, we're not really going to do much with that right now. But for those of you moving on to Calc 3, do know that you can get an area of a part of a polar coordinate by simply taking 1/2 from between two angles, that's why they're alpha and beta, of your function squared d theta. So if you had a point, suppose you had one of these petals and you wanted to get the area, I don't know, from pi over 3, oh, sorry, pi over 6 to pi over 3, you could get that area by applying that function. We'll put that out to 2 sine 2 theta. So you just apply it to that function. But we're not going to do that, but it's just something I want you to know exists for those of you that are going on to Calc 3.